This video is to introduce our work rethinking and improving the robustness of image style transfer. This work was done collaborated with Yijun and supervised by Nuno. We consider the image style transfer task. It aims to map a content image into a style of different reference image. An interesting consensus among existing work is that VGG as default feature extractor for loss computation and showing work well, but not other more advanced architectures like ResNet, DenseNet. Some previous work has found that VGG performs better in the sense that more style pattern can be transferred. Even a VGG with randomly initialized weight can produce comparable results to a pre-trained model, but this doesn't happen on other non-VGG like ResNet. This hints that the robustness is inherent to the architecture. In this work, we will explore why non-VGGs don't work well and try to propose a solution to mitigate this. Let's first briefly recall what is the basic style transfer. Given a content image, a style image, and a frozen network, we try to optimize the target image such that its activation close to that of this content image at a certain layer, and simultaneously multi-scale activation close to those of this style image on the gram matrix. Our work is based on a bunch of ablation studies on the architecture of pre-trained models and randomly initialized models. The latter is important to avoid loss of trainings. We choose ResNet as representative of non-VGG architectures and generate stylization results based on different architectures. More details can be found in our paper and supplementary materials. Here we show some core observations. Like we mentioned before, for random architecture here with prefix R, VGG is better than ResNet in the sense that more style patterns are transferred. The same observation for the pre-trained models. We did many ablation studies on the architecture. The main conclusion was that the poor performance of ResNet is merely explained by its residual connections. This is interesting since residual connections are usually seen as the main asset of architectures for tasks like classification. To provide evidence for this, we remove all residual connections of ResNet and found this dramatically improves style transfer performance and has much closer performance VGG than to ResNet. To further confirm this, we reintroduced the residual connections in VGG and it shows that this destroyed the performance. So we conclude that the weak ResNet performance is due to its residual connections. We next try to understand why residual connections are so nefarious for stylization. The method we use is to observe the evolution of statistics of activation map layer by layer. We found that the maximum value increase and entropy decrease gradually with layer depth for the architectures with residual. This is unlike the network without a shortcut where activations tend to decrease and entropy remain fairly constant and much higher. The similar behavior for gram values. There are at least two possible explanations following. The first explanation is inspired by the outlier sensitivity of L2 distance. Because the gram metric encodes the style pattern, if the maximum value is peaky, the optimization will only focus on peaky position and a few style patterns and ignore the remainings. The second explanation is from knowledge distillation. If we regard optimization as a teacher-student manner, the small entropy is more like a hard distribution that makes the optimization difficult. On the other hand, high entropy is soft and easier to optimize. We next investigate why residual networks produce peaky activations and gram metrics. We found it is because the specific design of residual connections where the addition operation is computed between the last BN and the reload layer. This makes it hard to suppress the growth of peaky value. To solve this, not to manipulate and change the original architecture, we pursue to smooth activations so as to decrease the maximum value and increase entropy. We found any mapping should work as long as it can smooth activation and increase entropy. So we call our method stylization with activation smoothing, SWAP. For example, just softmax activations. We evaluate SWAP on different non-VGGs and different stylization methods. It works effectively. In summary, in this work, we explore why non-VGGs work worse on style transfer and propose a simple yet effective way to mitigate it. The code is available online.